Welcome to this module on photovoltaic sizing and output. By the end of this module, you should be able to identify the main test conditions used in reporting photovoltaic output. You should be able to interpret photovoltaic specifications and labeling. You should be able to identify losses in photovoltaic systems and analyze solar gain with and without shading. In this lesson, we'll be discussing test conditions and photovoltaic labeling. In order to discuss test conditions, let's begin by looking at the need for a solar standard. Irradiance and temperature continuously change both during the time of day as well as seasonality. In order to have a standard for testing, as well as predicted output, the solar industry has developed a couple of standards for reporting module performance. We'll review those now. One of the test conditions that we've discussed before is known as Standard Test Conditions, or STC. Standard test conditions are defined as an irradiance of 1,000 watts per square meter and an air mass of 1.5 with a module cell temperature of 25 degrees Celsius. Another common test condition is known as Nominal Operating Cell Temperature, or NOCT. This is also sometimes called PTC, or Photovoltaics for Utility Scale Applications Test Conditions. NOCT is much more common. The NOCT conditions are an irradiance of 800 watts per square meter, an air mass of 1.5, and a cell temperature of 45 degrees Celsius, with an ambient air temperature of 20 degrees Celsius. NOCT also includes a wind speed of 1 meter per second. NOCT lowers the irradiance, which is a bit more realistic. You might notice that one of the major commonalities, though, between STC and NOCT is the variable of temperature. Temperature has a major impact on operating conditions, and we'll discuss this in the next lesson on array sizing as well as further into electrical code. At this point, it's only important to know that increasing temperature decreases the operating voltage of the module. We can also explore the practical differences between STC and NOCT conditions by looking at an IV curve. We learned how to read an IV curve in the previous module, where we evaluated maximum power, fill factor, and efficiency for a module. Note here that under STC conditions, a module would have a higher operating current and a voltage, thus producing a higher power. Under NOCT conditions, however, the operating current goes down because irradiance is lower, only 800 watts per square meter, and the voltage decreases because the temperature is higher, 45 degrees Celsius instead of 25 degrees Celsius. Because of those factors, the peak power is also lower. While these values are the same for the same module, NOCT conditions are a more realistic view that one could expect in the field. In array design, individuals do not rely on IV curves to calculate expected module performance under STC and NOCT conditions. Instead, some of the module manufacturers will show the STC and NOCT outputs in their own product labeling. In this case, a module STC is shown as having an average power output of 257.5 watts. However, at NOCT, the power is only 189.7 watts. So while this is helpful, product labeling is not universal, and the available information is not always identical. When performance under both STC and NOCT conditions are available, the installer has a better idea of what they would expect under real working conditions. So now let's look a little more closely at module labeling in photovoltaics. Module spec sheets generally focus on output data under STC. Let's start with this 255 series module, which has an average power of 257.5 watts. Oftentimes, the series name of a module is connected to the approximate power output of that module. Also note that some of the conditions we discussed before are shown, including the short circuit current, the open circuit voltage, the current at maximum power, and the voltage at maximum power. Not all manufacturers report module efficiency, but it's a very helpful specification. If you don't have it, you would have to calculate it yourself using the module power and the total area of the module. In addition to electrical characteristics, mechanical specifications will also be shown. Mechanical specifications include the size, the weight, the thickness, and the frame type, as well as the number of series cells within the module. These specifications are very important for a designer and installer, so she or he knows the space requirements for an array as well as the predicted power output. We've now defined STC and NOCT as well as some practical implications of those conditions. We've also looked at common mechanical and electrical module specifications on the spec sheets. In the next lesson, we'll learn how changes in tilt and orientation can impact electrical output for a module array.